Hi, my name is Kelsey Alder, and I'm going to be going through an unknown spectrum compound today. Spectral problem today, I apologize. So here is my PowerPoint presentation, and I'm going to walk you through the steps that I took. Okay, so the agenda are these 8 points. We're going to start with introducing the unknown compound and the group, followed by the calculations for the sites of unsaturation and possible relationships to the structures. Number 3, we will go through the IR spectrum and key structural features. Following that, the 13 carbon NMR, anisotropy and polarity relationships to chemical shift. Once we go through that, number 5, we'll go through the 1H NMR shift and demonstrate any evidence found on those signals, and then hopefully that will lead us to the identification of the correct compound, and then I will kind of sum it up with key points of the exercise and a conclusion at the end. I'm going to make sure this is recording because it stopped on me last time. Okay. Sounds good. So the unknown compound that I received was C10H12O in group 10. So here's a page for the sites of unsaturation calculations that I made. I just explained what each letter stood for, and then following that, I did the max number of hydrogens calculations using the 2C plus 2 formula. So that gives us 2 times 10 for 10 carbons plus 2 equals 22 hydrogens max in this compound. Calculating the sites of unsaturation here, I used the formula C plus 1 plus N divided by 2 minus X divided by 2 minus H divided by 2. And luckily there was no nitrogens or halogens, and so that gave us the formula of 10 plus 1 plus 0 over 2 minus 0 over 2 minus 12 divided by 2, which resulted in 11 minus 6, which gave us 5 sites of unsaturation. There were a multitude of possibilities that 5 sites of unsaturation could have created. I've tried to put the major points of what I thought could be potential relationship possibilities. So each aromatic ring would represent 1 site of unsaturation. Each site of unsaturation represents 2 hydrogens. And so a pi bond also represents 1 site of unsaturation, and a triple bond represents 2 sites of unsaturation. So knowing that, I said that there could be 5 double bonds or 5 rings, as well there could be 4 double bonds and a ring, or vice versa, 4 rings and a double bond. Then the combination of those following. So 3 double bonds and 2 rings, or 2 double bonds and 3 rings. A triple bond with 3 double bonds, or a triple bond with 2 double bonds and a ring, or vice versa, or 2 triple bonds with 1 ring or 1 double bond. So there are quite a few options here that we had. Let's see. Okay, here is the IR spectroscopy. So there's a few identifications that I made, but some of the major ones, well, I'll go through most of them. At 3000, this can indicate a CH stretch of an aromatic ring. Next to that, the CH stretch of an alkyl at 2900. It's not a very large absorption, but it is present. And then here at 1725, there's a carbonyl, a C-double-O bond that we learned a lot in class. And next to that, these 2 sharp peaks here can be indicative of a C-double-C bond in an aromatic ring. And then over here, I thought maybe this could have been some CH bending or a CO stretch of some kind at 1350 and 1150. So the 13C NMR spectrum, there were 6 unique carbon signals, 1, 2, 3, 4, 5, and 6. Starting at the upfield region, there were 2 signals there. These could indicate at 45 and 30 ppm. These could indicate alkyl groups like RCHR or RCH2R. They're more upfield, so they have more shielding and a higher electron density, and they have lower polarization because they don't have any double bonds or any large electronegative atoms connected directly to them or super close to them. Next to that, we have this middle section here. This can be indicative of a C double C bond, so alkenes, or a CH aromatic ring. There's 3 signals there at 140, 129, and 126. These have less electron density than the upfield alkyl groups, but more than the carbonyl group, which we're about to get to, due to these double bond potential in the aromatic ring or in the alkene. And next to that is the carbonyl group. It could, in this region, around 210 ppm, can often indicate a ketone present or an aldehyde with that hydrogen attached. This is the most polarized of these signals due to the oxygen that's present in the double bond with carbon. So it's a double bond and it's oxygen, making it the most polarized, and it has the least amount of electron density compared to the other groups. So continuing on, the anisotropy that I could identify were based off this aromatic ring or alkene signals due to the pi bonds. They were more deshielded, and it could indicate a potential benzene ring or a various collection of different compounds with an alkene group. But they are more deshielded, as I said earlier. And then next to that, in this potential ketone or aldehyde, they're even more deshielded, and there's a carbon, a double bond to the carbon-oxygen anisotropy relationship going on, creating its own magnetic field, pushing the ppm to a much higher level, both in those aromatic rings and in the carbonyls at 210 and around 120 to 140 in the downfield region. There was not as much anisotropy relationships going on that I could identify in the lower ppm in the upfield region from these alkyl groups. Okay, here's the 1H NMR spectrum. So what I could tell was there were 3 signals total. They were a little bit hard for me to read, so it took a little bit of guessing and figuring things out. But this first peak has an integration value of, well, let's start on the other side since that's the order I did it in. This peak here has 5 hydrogens, around 7.2. It is a singlet, and it can be indicative of the aromatic ring, which has come up in both spectrums prior to this, for a CH bond, and it's in a singlet. Next to that, we have this here, which can indicate 3 peaks. This could potentially show a CH2, 2 CH2 groups, because it has 4 hydrogens as its integration value, and the multiplicity is a triplet, meaning that it would neighbor an additional CH2 group or have 2 neighboring hydrogens of some kind next to it. And then following that, we have another singlet group in the 2.1 ppm region, which is often indicative of a CH3, like a methyl group, or something that doesn't have any other hydrogens bonded to it, so it could be next to a carbonyl, something like that keeps this peak on its own and doesn't have any neighboring hydrogens. Okay, so based on all of the information from those past, from all of these diagrams, the proposed structure that I thought from C10H12O that came to conclusion was 4-phenyl-2-butanone, otherwise known as benzyl acetone. And here we have the aromatic ring, which came up on each of our spectrums, each of the spectrums, the IR, the 13C, and the 1H spectrum. Here's the COO bond that came up. I'll go back early on here. Here's those CH stretching for the CH2 groups that I'll go back to. And here's the CH stretch at 3000 for the aromatic ring. This could be potential CH bending, maybe not a CO stretch. And then here could be the CCC bonds in the aromatic ring, as well as the COO bond at 1725. This shows the 6 unique carbons, which we can go back to on the diagram. I just wanted to rewind to kind of refresh the memory. And then here's our 3 peaks for hydrogen. So here's the CH3 group that showed up as a singlet with no neighboring hydrogens. Here are the 2 CH2 groups. So each has 2 neighboring hydrogens, since this is completely full. This carbon is completely bonded to other carbons. And so those 2 neighboring carbons would give you a triplet right here at about 2.8 or so. And there are 2 of those, which give you that integration value of 4. I forgot to say that if you add the 3 hydrogen, 4 hydrogen, and 5 hydrogens together, it will give you approximately 12 hydrogens, which was in our spectrum. And then the last hydrogens, well, right here, the last 5 hydrogens on this page have a singlet. This one confused me at first because I thought they would have a doublet, and then I realized that they have a singlet because they are equivalent in their attachments and in their chemical structures. So that was also a big indicator for an aromatic ring. Here's the ketone. Like I said earlier, it was a ketone, not an aldehyde. And yeah, I think that pretty much covers the whole proposed structure. The different carbon identifications, there's one here, second one, third, fourth, fifth, and then the 6th is these aromatic carbons right here. So that concludes why I thought that why this came to the conclusion of 4-phenyl-2-butanone. I hope you enjoyed the presentation and that it made sense enough for you. The conclusion, the key points of this exercise, in my opinion, were identifying unknown compounds using the IR spectroscopy, 1H NMR spectrum, and the 13C NMR spectrum. To put all of those together, using key points from each graph and seeing which ones contributed to very similar ideas and bonds, and pulling those similarities out and then creating a structure from that. I appreciate your time today, and thank you so much for listening.